In this video, we'll review some basics of feedback amplifiers. Let's begin by reviewing some notation. This is a picture that you may be familiar with of a linearized negative feedback amplifier. We're defining the input here as U and the fedback signal as V. The difference between them, X, is the input to the amplifier, whose gain is A, and then there's a feedback network with a gain beta. We define the loop gain L, sometimes called the open loop gain, as the product of A times beta. And then we can write an expression for the closed loop gain. That is the gain from U, the input, to the output of the feedback amplifier Y, with the feedback loop in place, as shown here. And you'll see that it's A over 1 plus A beta, but we can also rewrite this as A over 1 plus L. Now this is a very easy formulation to derive, but it's sometimes difficult to use in practice because there's difficulty in defining the gain of the amplifier A because it's often inextricably linked with the loading presented by the feedback network beta. Likewise, the gain at the input between U and the actual input to the amplifier itself is related to the feedback network beta as well. So it can be difficult to separate out A and beta. Therefore, we're going to find it useful to define the desired gain of the amplifier. You'll see that if we let the amplifier gain A go to infinity in our expression for the closed loop gain, we end up with simply A over L, because this term in the denominator becomes dominant, and we can ignore the unity term. And then we're simply left with A over L, which, if we cancel out A, we're left with 1 over beta. So this is the gain we would expect to observe under sort of ideal conditions where the amplifier gain A is very, very large. And so this gives us the sort of desirable property of feedback that the gain of the closed loop amplifier depends only on the feedback network beta. And so that's something that you may be familiar with. But we're going to flip this around and say, okay, so therefore, usually when we're designing a closed loop amplifier, we have in mind what we want the gain to be. That is the desired gain that we would achieve in the case of an ideal amplifier A. So knowing what that desired gain is, we therefore essentially know what beta must be. Secondly, the open loop gain L is something that's usually a lot easier to identify and determine than it is to isolate the gain of A alone. But if we know 1 over beta, the desired gain, and we can find the open loop gain, the loop gain L, which is the product A beta, then we can simply infer A from those two facts. There's no need to find A directly. So that can be a useful trick to keep in mind. Here's an example taken from the book, example 5.1, where we consider an amplifier with an open loop gain of 80 dB, a feedback factor of 1/5, and we see that the closed loop gain is in fact very, very close to 1 over beta, very, very close to 5. Another desirable property of negative feedback in amplifiers that you may be familiar with is that when the loop gain L is very large, much greater than 1, the closed loop system has an overall gain that's inversely proportional to the gain of the feedback circuit and highly insensitive to the gain of the amplifier A. So again, small changes in A, delta A, give rise to relatively small changes in the overall closed loop amplifier gain, delta A closed loop. And you can see that here because the change in A is divided by the loop gain squared here. This expression here is an expression for the gain sensitivity of the closed loop amplifier. And you can see, for example, following through in the same example as the last slide, where A had a nominal gain of 80 dB, that even if A decreases by an entire order of magnitude all the way down to 60 dB, the closed loop gain changes less than 0.5%. Two other benefits of negative feedback in amplifiers are bandwidth extension and an improvement in linearity. So for example, we can consider bandwidth extension by writing the frequency response of the closed loop amplifier as a function of the desired gain 1 over beta and the loop gain L. And most often in cases of interest, to us, the amplifier's frequency response will be monotonically decreasing, as plotted here, whereas the feedback network beta will have a relatively constant response over frequencies because it's often going to be just a network, a passive network that has a much higher bandwidth than the amplifier A. So in cases like this, we've got at low frequencies, L being much greater than unity, and hence this term here just approaches unity, and we end up with a closed loop gain of simply 1 over beta. So even as A may be varying over frequency, as long as L is much greater than 1, then the closed loop response stays very close to its desired value of 1 over beta. Then, with this monotonically decreasing A and L with frequency, at some point, L is going to equal 1. This is the so-called unity gain frequency of the feedback amplifier. And at frequencies beyond that, we're going to see L much less than unity. And then in that frequency range, instead we're going to have L being negligible compared to this term 1 in the denominator, and we're going to end up with a closed loop response that simply looks like L over beta, which can be simplified to simply the amplifier gain A. So beyond this unity gain frequency, we've got a closed loop response, ACL, that begins to follow the amplifier's response A. But looking at these two plots, you see clearly that the closed loop response has a much higher bandwidth than that of the open loop amplifier A on its own. So it's this classic trade-off where we sacrifice gain in order to have the gain being better controlled over a wider bandwidth. At the same time, we saw on the last couple slides that the input to the amplifier itself is much smaller than the input to the feedback amplifier, U. Specifically, the amplifier is exposed to signals that are approximately L times smaller than would be the case without feedback. So whenever you've got a nonlinear amplifier exposed to very, very small signals, then our linearized small signal approximations apply, and the approximation is much better. So in a sense, the amplifier as a whole starts looking more and more linear. The feedback network may be exposed to large signals, of course, but since it's another reason why we're going to generally implement it as a simple passive network, making it linear even over very large signals. Just as an example of when thinking about the desired gain can be useful, a very simple example is provided by the inverting configuration here. It's a very simple amplifier configuration, but in order to do a rigorous feedback analysis of the circuit, you typically have to apply a source transformation here between Vs and Z1, transform it into its Norton equivalent, and then analyze the remainder of the circuit as a kind of a transimpedance amplifier because it's a shunt-shunt feedback. So that's a little cumbersome, and especially considering this is one of our simplest feedback circuits. Instead, another way to think of it is to simply recognize that we're all very familiar with the fact that the desired gain of this circuit is negative Z2 over Z1. So therefore, we can write the closed loop gain in this form if we think of this term over here instead of 1 over beta as being the desired gain. And so knowing that 1 over beta is negative Z2 over Z1, then we simply see that the closed loop response of this inverting configuration looks like negative Z2 over Z1 until such frequencies where this term here, L over 1 plus L, starts deviating from unity. So that brings us to our next point where we recognize that the amplifier's closed loop gain depends only on the desired gain and the loop gain. So again, writing the closed loop gain in this form, we see clearly that we've got the desired gain, which is generally constant over a very wide range of frequencies. And all of the frequency dependence is captured by the second term here, where we see only the loop gain L. So the closed loop amplifier's dynamic response, everything about its dynamic response, its bandwidth, its step response, its phase margin, etc., can be obtained from knowledge of the loop gain, an analysis of the loop gain L, which is relatively easy to find, both in simulation and through hand analysis. So just a reminder, how do we obtain that loop gain L? Well, let's imagine a very general picture of a feedback circuit here. That can be whatever you want in these boxes. There's an input coming in on the left. The output of the circuit may be considered over here, or in some complex situations, you may actually be using multiple outputs from the same feedback loop. You may be using a node here for maybe doing something useful for you, and as well as this node, these nodes here may be doing something useful for you. None of that matters when you're finding the loop gain L. The procedure is simply you set all independent sources to 0. So that means if you've got any independent voltage sources, you set them to 0, they become short circuits. If you have an independent current source, you set it to 0, and therefore it becomes an open circuit. The second step is that you select the place to break the loop and terminate it with an appropriate impedance. So, for example, we may select this point in the feedback loop here. We break the loop, break the connection, and we apply a termination impedance here. We connect ZT so that to be equal exactly to the impedance that we would see looking this way into the remainder of the feedback loop. And then finally, we insert a test signal at the break. It can be either a voltage or a current signal. And we look at the returned voltage or current signal across this terminating impedance ZT that we introduced. And then the loop gain L is simply the response from the test source to the returned signal here. If we apply a voltage test source, we have to look at the returned voltage. If we apply a current test source, we have to look at the returned current. That way L is always dimensionless. This procedure is amenable to circuit simulation. The only catch here is that in addition to taking care to terminate the loop properly, you also want to take care to not disturb the circuit's DC biasing when you break the loop. This is no problem when there's only passive components involved, but as soon as you've got active components involved, you have to keep in mind that all of this feedback analysis is predicated on a linearized assumption of the circuit. And since transistors, for example, are very nonlinear, really all of this only applies to the small signal circuit, the equivalent small signal circuit. So if we're doing this in simulation, we are going to be breaking a loop, and so we have to make sure that any transistors in the circuit are still biased at the same operating point that they would be if the loop were closed. That way the linearized small signal equivalent circuit stays the same when we're finding L. Yes. Finally, it's good to keep in mind that there's a subtle approximation being made when you use this procedure, and that is that essentially signals only circulate in one direction around the loop. Right? So we can apply, by breaking the loop, we're applying a signal here and only looking at the return voltage this way. In principle, a signal introduced here may also result in a return voltage the other way going around the loop, and that impacts the feedback circuit's analysis here. But in the typical case, the gain in one direction will be much larger than the gain in the other direction. As long as we have a unidirectional amplifier somewhere in the loop, then this approximation is quite useful. When it comes to terminating the loop with an appropriate impedance, it can be really worthwhile to take a bit of care in deciding where you want to break the loop. If you break the loop at a convenient point, that can make terminating the loop a really trivial exercise. So for example, consider the inverting op-amp configuration shown here. We've taken the op-amp circuit itself and replaced it with a linear model for our analysis. The differential input to the op-amp is Vi across these two terminals here. it's got a frequency dependent gain AV and an output impedance ZO. Now, if we break the loop as shown here, our op-amp has a very high input impedance. So essentially, we can terminate the loop with a very, very high or infinite impedance as shown here. Having broken the loop there, we introduce our test source VT here, and we can do the analysis for L, and that's carried out over here. Another more complicated example is presented here. It's essentially a single stage CMOS differential pair with active load followed by a source follower Q5. So this is a unity gain buffer essentially with negative feedback arising here, where the output is fed back to one side of the differential pair and the input comes into the other side of the differential pair. Now remember again that when we're doing our analysis for L, we're implicitly assuming a linearized circuit analysis. So we have to take small signal equivalents of everything. So here we have small signal model for the differential pair with active load. And then we've got small signal model of the source follower, Q5, shown here. So schematic B here is a small signal model for schematic A. And then we can do our analysis for loop gain L by breaking the loop at this point. Doing so, we've got a relatively high impedance looking this way. We've only got the gate capacitance of the differential pair. So on the bottom, we've broken the loop, introduced our test source VT, and we've applied a capacitance 1/2 the CGS of the input pair transistors Q1 and Q2. So we terminate the loop there. If we're a little bit off in our estimate of CGS, it hopefully won't affect the analysis too badly because in a lot of cases, CGS would be quite a bit smaller than the load cap CL anyway. So again, this is an example where we've chosen a convenient place to break the loop that hopefully won't disturb the analysis. So this schematic shown here on the bottom is useful for our hand analysis, and that's what's shown over here on the right, arriving at an expression for the loop gain L. The analysis is performed only at DC for simplicity, so the capacitors are not included. If you include the capacitors, obviously there'll be a lot more terms, including the frequency-dependent impedances of the capacitors. And again, just a reminder that if you wanted to instead perform this analysis in simulation, you would be breaking the loop here, and you would have to take care in doing so that you somehow maintain the DC bias on the gate of Q2. So again, just some practical tips for simulating the loop gain L. And again, one of the main issues here is that the definition of loop gain presupposes linearity of the system. And so when we're simulating loop gain, we have to somehow break the loop while still preserving the circuit's true DC bias operating point. So one way to accomplish this is shown here. We're breaking the loop at this point, and we're breaking the loop with a very large value inductance. And when I say large, since you can introduce an ideal inductor in simulation, you want to make it have an absolutely huge impedance at any frequencies that you're interested in. So you could use 1 Henry. There's no reason not to, right? So a huge inductor value like that will still have zero impedance at DC when the simulator is performing its DC operating point analysis around which it'll linearize the loop. But at any frequency that you're interested in, if you choose a huge inductance L, this impedance will just be massive and will look basically like an open circuit. At the same time, we've introduced our test source here, VT, and we don't want it to disturb the operating point for the DC operating point analysis here. So we introduce a capacitor here so that at DC, VT is not connected to the circuit at all. And so at DC, we will basically have the loop closed and the DC operating point will be calculated properly. But we capacitively couple the test source in with an absolutely huge coupling capacitor C, so that again, at any frequencies that we're interested in, this capacitor will look essentially like a short circuit, and VT will be coupled directly into the test point that we've chosen. And finally, don't forget, we do need to introduce the terminating impedance, ZT, over here. If ZT is not purely capacitive, you may wish to introduce a large AC coupling capacitor here as well, so that it doesn't disturb the DC operating point analysis either. Here we consider another classic case of negative feedback amplifier, the non-inverting op-amp configuration. Again, we can start out by thinking about what's the desired gain of this circuit. That's the one obtained when the op-amp's gain becomes huge. And we know very well that the desired gain of this non-inverting configuration is 1 plus Z2 over Z1. So we know that 1 over beta can be thought of as our desired gain. And here's another way of writing 1 plus Z2 over Z1. So therefore beta is the inverse of that, Z1 over Z1 plus Z2. And that's, also not that difficult to analyze for. It's simply impedance divider across the feedback network formed by Z1 and Z2 as well. Here's a linearized schematic of the non-inverting configuration shown here, where we simply replace the op-amp with its linear model, having input impedance Zi and output impedance Zo, and frequency-dependent gain, AV. Here we're proceeding with our analysis of the non-inverting amplifier, trying to find the loop gain. Again, we need to set the independent sources to 0. In this case, there's just the input source Vs. Setting it to 0 is tantamount to replacing it with a short circuit. So that's done here. And we've chosen to break the loop here. Actually, for this analysis, we can do so right inside the op-amp at the output of the dependent voltage source. And the reason it's convenient to break the loop here is because if we break the loop right at the output of this ideal dependent voltage source, then it doesn't really matter how we terminate the loop, because it's an ideal, it's being, whatever termination impedance ZT we need to introduce here, anyway, it's being driven by an ideal voltage source. So it doesn't matter, we don't have to get that right in any way. So that's convenient. And then in that case, we introduce the test source VT here and look at the returned voltage back coming out of the dependent voltage source. So doing the analysis in this way, we can just redraw the schematic as shown here. It becomes very, very simple, just series of passive voltage dividers across various impedances in the circuit, followed by the dependent voltage source gain. That's the op-amp's frequency dependent gain, AV. And the expression comes pretty straightforwardly here. Now, although the complete expression for L is quite complicated, it simplifies considerably under the common case where the input impedance of the op-amp itself is a lot greater than the other impedances connected at the input, Z1 and Zs. And if the output impedance Zo is quite a bit smaller than the the impedances connected, the other impedances connected at the op-amp output. And then we get this simple expression, which is what, it's pretty intuitive. It's just the op-amp's frequency response AV times the basically the beta, the impedance divider formed in the feedback network. Continuing on, here's another example that's very commonly encountered. It's a unity gain op-amp configuration. This can be thought of as just a special case of the non-inverting configuration, where the feedback network impedances are 0 and infinity. So Z1 in the non-inverting case is just replaced with infinity here. Z2 is replaced with 0 or short circuit. And then making those substitutions into the expression for L derived on the last slide, we basically very quickly get the result shown here. Now the desired gain of this configuration is obviously 1, so the closed loop gain is simply the desired gain, 1 times L over 1 plus L. Substituting in the expression shown here for L gives us this relatively simple expression here, And you can see right away that as long as the op-amp gain, AV, is very, very large, then these two terms in the denominator become negligible, and we get our expected closed loop, or a desired closed loop gain, simply unity, by ignoring those two terms. So that's good reassurance that the analysis has been done properly. Now, finding the output impedance of a closed loop amplifier in the presence of negative feedback can be a little bit one of the more complicated aspects of feedback amplifier analysis. So here's just a little trick, a little technique that can be useful. It can sometimes make your life easier in that regard. And we'll look at the technique by applying it to the unity gain op-amp configuration that we just considered. So if we're interested in the output impedance here, one way to do that is to recognize that when the load impedance is infinite, then certainly we expect the closed loop gain of this amplifier to be very, very close to unity as long as the op-amp has a high gain at DC. So we know that if the load impedance is then reduced from infinity to a much lower value, we will start to see the closed loop gain, even at DC, decrease because a voltage divider is formed between the output impedance of the closed loop amplifier and the load impedance ZL. Now, at some point, if we keep reducing the impedance ZL, we will see that the closed loop response will drop all the way to 1/2 of the value observed when ZL was infinity. And at that point, we would know that ZL is precisely equal to the output impedance, Z0. Perhaps that's most easily seen by, imagining that we can replace this closed loop amplifier with an idealized or model of it that has a gain of very close to unity and an output impedance Z out. And then that's loaded by our load impedance ZL. So when ZL is infinity, then we would just see the ideal gain of the closed loop amplifier, unity in this case. But when ZL equals when ZL equals Z out, then we'll have a voltage divider with a gain of 1/2 formed between these two impedances, Z out and ZL. So the closed loop amplifier gain will drop to 1/2 of its nominal value when ZL is exactly equal to Z out. So we can make use of that fact, both in analysis and in simulation, to find the output impedance. We simply solve for the case where the gain is 1/2 of the value that we expect to observe when ZL is infinity. So in this case, we take our expression for the closed loop gain and we solve for the Z out that would result in that gain equaling 1/2. And it turns out that the value is shown here. So, and the interesting fact here is that the output impedance of the overall closed loop amplifier is much smaller than the value of the output impedance of the op-amp on its own. It's reduced, in fact, by a factor close to the loop gain, AV minus 1. Here we return to the example of the inverting op-amp configuration. And again, this is often modified slightly by making a source transformation and converting the input into its Norton equivalent, as shown here, in which case the feedback amplifier looks like a transimpedance amplifier with shunt feedback. But the good news is that in either case, when we're finding the loop gain L, the result is the exact same. And in fact, the analysis looks very much the same as it does for the non-inverting configuration, because the first step in finding the loop gain L is to set all independent sources to 0. So in the case of this example here, we would set Vs to 0. That shorts that node to ground, and you end up with the same circuit to analyze as we found for the non-inverting case. Over here, if we set Is, the independent source, to 0, we basically replace it with an open circuit. And again, in any case, we always end up with the same schematic. And so therefore, the analysis for the loop gain L is very much the same in all cases, and the results shown here in the bottom right. So next, we'll just begin with a little background review on stability of negative feedback amplifiers. And I assume that most of you would be familiar with stability analysis of feedback amplifiers using Bode plots, where we plot the frequency response of L, both its magnitude response and its phase response. We look for a key point, specifically the unity gain frequency of L, the point at which its magnitude response is equal to unity or 0 dB. And then considering the phase response at that same frequency, we're looking for some phase margin. That is, we're looking for the phase response to be above negative 180 degrees, and the amount by which it exceeds negative 180 degrees is the phase margin of the feedback amplifier. So I assume you're generally familiar with that, but I just want to take a step back for a moment and just remind you that all of this analysis we do using Bode plots is really built upon Nyquist stability analysis. So remember that the Bode plot is just one way of representing graphically the frequency response of L. Another way is to plot both the magnitude and phase simultaneously on a polar plot. So that is what the Nyquist plot is here. And so you'll see here that as we start at DC, we've got a very large magnitude response for L and a phase of 0 degrees. So that puts us on a polar plot over here on the positive real axis. And then as frequency increases, we trace out this solid dark black line because the phase response starts going negative. So we go to negative phases, and the magnitude response starts gradually decreasing, and the phase continues to decrease even past negative 180 degrees. But by that point, the magnitude of L is below unity, so we're inside the unit circle here, and it just spirals in towards the origin. So this is the case for the sort of simple feedback amplifiers that are going to be our initial focus here. Moreover, we're focused, it's really a very unusual case where L is itself unstable. That's not exactly the same as a closed loop. It's not actually at all the same as the closed loop amplifier being unstable. But we're going to, the vast majority of cases that are of interest to us, we're beginning with L, a response for L that is itself stable. So in a case like that, really what the stability criteria is that this polar plot, the so-called Nyquist plot of the frequency response of L, shall not encircle the point -1 in the complex plane. Okay. So shown on this plot here, the phase margin is really the point at which the Nyquist plot crosses over inside of this unit circle. And for the simple type of frequency response plotted here on the left, L is monotonically decreasing. So once it crosses within this unit circle, it never goes back out. So as long as that happens, before we pass negative 180 degrees of phase, then there's no way it's going to encircle the point -1, and therefore we'll stable. So that's what our basic Bode stability analysis, our simple Bode stability analysis is based on. But you can imagine a strange frequency response for L, where it has a phase shift of -180 at some frequency, even with a magnitude response over 1, but that then it comes back to a phase response above -180 before crossing over this crossover frequency where the magnitude response is equal to unity. So you could imagine, just to be clear, Nyquist plot that looks something like this, in principle anyway. And that, would, strictly speaking, that would be stable. That would represent a stable feedback system. And you may encounter, down the road some strange situations where your intuition about stability derived from looking at the Bode plot alone may fail you. Okay, so I think it's always good to have in mind what are the assumptions that underlie our understanding of these simple criteria. But again, obviously Bode frequency, response analysis for stability does work. In the majority of cases that we're interested in, we're talking about negative feedback amplifiers. And that's because L is monotonically decreasing. And moreover, the phase response is generally going down. So some more definitions here. Omega with a subscript T, that's our unity gain frequency, which is the frequency at which the loop gain L equals unity. It's not the same as the frequency where the amplifier's open loop gain equals unity, because the feedback network, of course, is included. Beta is included in L. The phase margin, therefore, is simply determined by evaluating L at the unity gain frequency omega t and looking how far above negative 180 it is. That's our phase margin. And we can get some other interesting facts here. Since the magnitude of L at omega t is unity, and then we know it's simply given by, can be written as e to the j theta for some angle theta, which is L's phase response at the unity gain frequency omega t, and is therefore related to the phase margin. So substituting this expression for L evaluated at the unity gain frequency into our expression for the closed loop response allows us to find the closed loop response at the unity gain frequency. Right? So we've substituted in our expression for L here and here. And what you find if you take the magnitude of this expression here is that the closed loop magnitude response evaluated at the unity gain frequency is related to the desired gain 1 over beta. So that's what we would expect to see at low frequencies. And there's this extra term, this 1 over square root 2, 1 minus cos theta, that depends only on the phase margin of our system. So this is very interesting. It turns out that, it's very simple criteria. We can place on theta, to ensure that this term never goes up above 1 over beta, right? And so, what we find is that for theta, 60 degrees, with a phase margin of 60 degrees or more, that this term here doesn't exceed 1 over beta. And the situation is a little more complicated in that the closed loop response may exceed 1 over beta at some other frequency, not the unity gain frequency. But this clearly allows us to see that the phase margin is directly related to the amount of peaking that we see around omega t in the closed loop magnitude response. So this brings us to the final point here, which is that I've always thought that phase margin is an unfortunate name because it immediately suggests to us as engineers that phase margin is a kind of a safety margin that we want to see just to make sure that the feedback amplifier never goes unstable. That sort of implicit there in our thinking is that, well, a phase margin of 5 degrees would be fine. The only reason we shoot for a phase margin of 60 degrees or 70 degrees is just to be really, really sure that no matter what happens, that we've got at least a few degrees of phase margin. But that's not at all the case. Phase margin is, a phase margin considerably more than 5 degrees is absolutely required in most cases, just to ensure that the amplifier behaves in an acceptable manner. So it's not enough that an amplifier simply be reliably stable. It's also must, in general, reliably have a relatively large phase margin. So we've already seen, for example, from the expression we derived on the last slide, that If we have a phase margin less than 60 degrees, then the closed loop response plotted here in the solid line will go up above its low frequency value, 1 over beta, at the unity gain frequency omega t, whenever the phase margin's less than about 60 degrees. Okay, so that may be very undesirable, right? That means that we've designed a closed loop amplifier to have a gain 1 over beta, but that over some frequency range, it's actually got a gain higher than that. It's sort of expected that at high frequencies, we're going to lose gain because of the finite bandwidth of the amplifier, but peaking in the magnitude response in some applications is going to be very undesirable. And other undesirable phenomenon may arise when we have small phase margins. So that's the real reason why we specify large phase margins. 60 degrees, 45 degrees, 80 degrees, even 90 degrees is not just as a safety margin, but it's actually to make sure the amplifier's dynamic behavior is meeting the application's requirements.